Dun, dun, dun. Okay, now we are recording, so that's good. Okay, so where we left off was talking about APIs and stuff, and now we're done with that. And what we'll talk about is Google's databases and some related topics. So I'm sure you all know that Google is super big, and they have lots and lots and lots of databases for all the massive amounts of data that Google holds, right? So there's advertisements, there's user responses to ads and search results, right? Google has to track all that dynamic. Cached web pages, web analytics data, right? All of this stuff, because Google has its web analytics platform that it offers for free, and so it has to store all that data somewhere, and whole bunches more. Now, that's fine. So a key takeaway, Google has a lot of databases because they have a lot of different kinds of data, and they keep, the system separate. But what may be surprising is Google's advertising runs basically on an extended relational database or SQL system. Now, it's not just plain vanilla basic SQL. It's something called NoSQL that adds on some new properties, but fundamentally it is a relational database system, which should surprise you. Should surprise you because this whole semester we've been talking about how when you have lots of different kinds of data or the data itself is varied in some sense, relational databases are not generally a good choice. Well, let's think about advertising. Some advertisements might just be text, some might be images, some might be videos. You don't want to keep all of those in the same database table, right? Because that would be wasteful. You would have, some entries being very, very small relative to the videos, you have some being very big. But what Google can do, number one, these advertisements are in a standard format, right? So if Google's showing an ad somewhere, it's fitted to a particular size. And so any image of a certain resolution, that can be stored in one database table where every record is known to be the same size. Likewise, even though you might have videos where like one is 5 seconds and one is 2 minutes, if Google chops up that video into segments and stores the pieces of the video as separate records, then guess what? Then, maybe you're having 1 second segments for each. And so that 5-second video takes up 5 records. The big video, which normally you wouldn't want to have big and little videos in the same table, that big video becomes a cluster of 120 segments or records. So anyway, there's some various tricks that Google can use. Part of what's inherent in the data that they get, there's some similarities built in, and then some tricks like segmenting videos, Google can also apply that. So even though you might not think relational databases are a good idea, actually Google can operate them pretty efficiently. Now, the two databases that are relevant here, number one is Spanner. Spanner is so-called because it spans Google's entire operation. It's the base database for a lot of different stuff, both within Google and for cloud services that Google offers. On top of Spanner is the database system holding the ads, which is called F1. So let's talk about F1. First of all, F1 is a very big relational database system. Okay, so like the stuff we did in Access, just a lot bigger. And there is some more to it. Like NoSQL databases, it is scalable to run on many instances of standard hardware. So let's talk a little bit about relational, I'll push that off. We'll talk in a moment. So operational properties, think of this advertising database as being a lot like Facebook's Haystack, right? Stuff gets uploaded once and it can be read many, many, many times, right? The advertiser uploads a video once. Whenever Google needs that ad to be shown along with some search results or elsewhere, it pulls that video from the database. So it doesn't matter that much if it takes a little time to upload data. It doesn't matter much if write operations are slow. What matters is that read operations have to be super fast, okay? Because that's the kind of database that this is. The other thing, again, ads are stored in standard formats. So, this is basically compatible with our relational database system that we've talked about. So again, you want to have records be approximately the same size, right? They don't have to be the exact same size down to the byte, but you don't want to be wasting a lot of storage space, right? You don't want to allow a field to have, room for a, 2 gigabyte video if most of the videos that are getting stored in that are, only a few megs. All right. Now, Spanner. Spanner is Google's system. Again, it uses SQL, but it approaches NoSQL performance levels. All right, so this is an interesting thing, and let's talk about it for a minute because it's kind of magical and because we have time. So there's something in databases called the CAP theorem. Okay, and the only reason I bring it up. Okay, so the CAP theorem, this won't be on the exam, so this is just, fun context. The CAP theorem basically says that if your system gets partitioned, right, basically say network traffic interrupted, right, which is bound to happen in a big system. If you have a big system that is on multiple separate machines, in practice, you can't guarantee that it's all the different components are always going to be connected. There are various things that can go wrong at various times. So if your system gets partitioned, you have the option of either one, delivering outdated data, right? So if somebody enters in a query and your system is partitioned, there might be newer information stored elsewhere in the system that can't get to the part where the question is being asked, okay? So that's one possibility. If you say, well, we're going to fulfill this request as best we can, even though we know it might be out of date. Or the other option is you could send back some kind of error message or wait for the connection to be restored. Okay, basically availability, consistency. This one emphasizes availability, that your database is always going to give you something, but you can't guarantee that it's going to be, absolutely up to date. Or you could emphasize consistency and say, we're not going to give you that result until we're sure that it's the, newest result available in the case of a partition. Okay, this is what the CAP theorem says. And Google's system, Google's Spanner in particular, essentially jumps past this problem, which is kind of magical, right? And basically the way Google does it is, number one, lots of backup connections, right? Backup data and connections. And number two, super fast because RAM instead of disk. Okay, so Google has a lot of data. If most database systems are designed that they keep most of the data on disk and they only pull it out when they need to. Well, Google, number one, they can afford a lot of RAM, so they can have, a bigger system with all that. But number two, they have a really good idea of what data is going to be relevant at any given point in time. And so they can actually use that RAM really effectively so that they don't have to store their entire system in RAM, but just about everything that's likely for anybody to ask at any given time, they can serve that up really fast in Spanner. Okay, so anyway, we'll have a picture on the next one. So again, not on the exam, but Google's kind of magical, right? In the industry, people look at this and say, wow, how does Google even do this? It's amazing that they provide very strong availability and very strong consistency guarantees. So in a distributed system, meaning it's all sprinkled out over multiple machines and data centers and such. Okay, so again, Google Spanner provides almost immediate consistency as a distributed system, right? So essentially, it follows these ACID properties, right? There are places where it cuts corners, but very strong consistency guarantees as far as transactions, which is important because if Google's saying to businesses, hey, put your stuff on our cloud, we want to handle your transactions for you, the business have to be really confident that no data is going to get lost in the shuffle like that Bitcoin hack, right? Businesses want to make sure that any financial transactions go through correctly and all that. So as far as that goes, they got to follow ACID properties. But as we've talked about, when you follow ACID properties in a very large system, it tends to slow your system down significantly. But part of the magic of Spanner is each individual business can operate concurrently with all the other businesses, right? So if you have a transaction for one business, one customer, sure, you have to isolate that from all the other transactions with that same customer and business, but you don't have to isolate that business from all the other businesses that might be selling stuff on Google at the same time. So they kind of get around that problem. Anyway, the other thing, so it uses SQL. Big reason for that, Google's trying to bring businesses on board to use the cloud service. And what would happen if Google says, well, we have a really nice cloud system, but you're going to have to update all your database code because it uses something different from your standard SQL. And the businesses will say, well, that's great, but it's going to be really expensive to rewrite all of our database code. And then we got to take time to test it to make sure we didn't add in any bugs, or more correctly, to find the bugs that we did add in and then hope for the best after that. So Google wants to make this system use ordinary SQL so businesses can just show up with their databases written the way they are, migrate them over to Google, and have them work correctly, okay, and not have to worry about any problems with that. So as a cloud tool, it enables businesses to migrate their databases as is, retaining ordinary SQL code. All right. And now we get the promised picture. So basically the two axes there, speed and flexibility, that's what your NoSQL systems tend to provide. So think of something like, I don't know, what do we want to say? Let's say there's a couple ways that NoSQL systems can cut corners, right? One is Facebook's Haystack. So with Haystack, you are not really able to do queries across tables, right? For however data is stored in there in terms of tables, you can't say, run some query to say, dear Facebook, let me find the entire list of photos that were posted by people in Chicago during the month of March 2023. You simply can't run that query. Right now, you could run the query if you had the code for it and access, but it would be really slow because the system just isn't set up for that. All of the photos are on different machines. All of the users are on different machines. It's really not set up for that kind of process, even though the data is there. So when we say fast and flexible, but some applications can't tolerate inconsistency. Another one is Facebook posting, right? We talked about eventual consistency for Facebook, the idea that if you make a post and that post is echoed to 2 data centers, the likes and other emotes for that post, they're not reactions. They're not going to be closely coordinated down to the split second because it's not that important if data center 1 has one list of users who liked your post and data center 2 has another slightly different list. It just doesn't matter that much. Facebook will get around to catching up. But like we talked about with the Bitcoin hack, for transactions, that stuff is absolutely not okay, right? That's how millions of dollars in Bitcoin walk out the door. So we say some applications can't tolerate inconsistency. Well, banking applications, various financial transactions, stuff like that, you want to be absolutely sure you're following ACID properties for those. Okay, but NoSQL systems, they can do stuff faster because they cut some of those corners. Now, traditional relational database systems up in the upper left there, great as long as the data isn't too big, right? The big thing is, as long as you can take all of that data you have and put it in RAM, it's probably going to be pretty fast, right? But as the databases get bigger, start spreading out to more machines, then it becomes a big hassle to implement any kind of change in the database setup, right? So if you're doing Microsoft Access, for example, and you want to add on a new field to a database table, as long as you don't require that every record has some data for that field, it's not a big deal, right? You just go in there and boop, make the new field, and there it is. But if you're talking like a big system where it's all the database tables are already spreading across many, many pieces of hardware, then adding a new field is going to require a lot of careful recalibration of the whole system. You're going to have different setups of what tables can be, what portions of what tables are stored on what machines. You may have to re-engineer which parts of the tables are optimized in the fastest parts of whatever machine, right? Some things that were cached in RAM on one machine will now have to be cached on another machine, stuff like that. So in a big system, it's a lot of work to make any kind of changes like that, but it will give you correct results, right? Traditional relational databases do follow ACID properties. You get the correct result, it just might be slow and it's going to be hard to change. So Spanner tries to get the best of both worlds. What it does, number one, it's fairly easy to make changes because Google's got that set up. And the basic idea there, Google's really big. They manage a lot of data all the time. So a problem that might seem like a big data problem to, I don't know, say New Balance shoes, for example, seems like a big data problem to them. Google's going to look at that and say, no big deal, we'll handle that, right? So problems that are big to small, medium, even maybe somewhat large businesses can often be trivial to Google. So it's easier to do that. And number two, because Google's system is super fast, basically, I'm going to lift that image. Because Google's system is super fast, they can provide consistency guarantees a lot better too. So what should really be here is there should be a third axis that essentially says cache. I wanted to do that in green, which just means if you have enough money to buy a whole lot of RAM, then a lot of this problem with consistency and speed and flexibility, that trade-off kind of goes away, right? Because the problem with speed and flexibility, if stuff is in RAM, it's easy to change. If it's spread out on different disks on many different machines, yeah, then it's a lot of work to change your system. Likewise, consistency guarantees. If stuff is in RAM, it's going to get finished, any transaction is going to happen in, a fraction of a microsecond. So even if your system gets pretty busy, if you have enough cache to put basically all your active data in RAM, boom, that problem goes away too. Okay, so again, consistency, speed and flexibility, and cache. But if you don't, if you're limited by more conventional cache constraints, then yeah, this trade-off is pretty much what's there. Okay. All right. Questions? Anything? Would you like to know more? Well, if that was sufficient? Okay. Now, so we've talked about F1, we've talked about Spanner, and now the time has come for us to talk about BigQuery. And BigQuery, as you might guess, is a system that allows you to do queries on very large tables, what you might call big queries. Okay. Now this system is very, very big, and if you're interested, there's some, some information in there you might be interested in reading. But fundamentally what it is, there's a lot of businesses that accumulate data, but then it's easy to store data, right? You just load up hard drives, and once you've loaded up one hard drive, you load up another one and whatever, then you're done. But at some point, it becomes difficult to extract meaningful information from that, all those hard drives, right? You have to come up with, if all of your data is stored on one disk, yeah, you can find it. But imagine you have so much data that it's on, hundreds of different disks. You have to set up a specialized system in order to run queries on that in any kind of reasonable speed. So a lot of businesses have this where they have tables that are, millions of records long. Again, something like Facebook, not saying Facebook uses BigQuery, but Facebook has billions of monthly users. If it wants to do any kind of query on that entire list, it's simply not going to do that on one machine. It's not going to do that on one standard off-the-shelf piece of software like Microsoft Access. So in order to do those very large queries, you do need some specialized systems. And for the vast majority of businesses out there, right, they're not going to design that kind of system themselves. It's a lot better for them to say, oh, Google has something we can use. We know it works. We show up and use it. We don't have to worry about building it or maintaining it or debugging it, any of that stuff. Okay. So this slide, again, this is another thing not going to be on the exam, but hopefully gives you some useful content, useful context about what we're talking about. So relational databases, the relation in relational databases means those linkages across tables, right? You guys probably remember doing that in the homeworks, the lab exercises, whatever. That's the whole point, is that you can ask the table, hey, show me all the invoices by all the customers who live in Chicago, right? And you can have one list of invoices, each of which contains a customer name, and a list of customers, each of which contains the address. And you can link those two tables together to give you all the query results, that fit your criteria. Now, so that's what a join operation is. Any kind of operation that brings together data from two tables or joins the tables. Now, there are different kinds of join operations, though. And one thing you have to understand for this is your standard database software likes to pull all the data it needs and basically construct sort of a mega table of that data. One of these links here, if you're interested, can discuss how that happens. But there's a specific kind of join called an outer join, where you're basically cross-checking every value of a field that appears in one table and verifying that it exists somewhere in the other table. Basically, you're saying that for any record in table 1, if there's a field there, that value from that field is present somewhere in the other table, right? That's that referential integrity thing that you might have clicked a checkbox for that until you realized it was a nightmare if you did. Okay, so that kind of operation called an outer join essentially results in multiplying the two tables together. And if your tables are already very large, multiplying two large tables gives you a very, 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 very super large table, right? So if you had two tables with 1 million records each, multiplying them together would give you 1 trillion records in that, that mega table that gets constructed by the database software, which again, may not even be feasible to do on one machine. But if all that data is on separate machines, then instead of even having that operation happen at RAM speed, it's going to happen at network speed, which is going to be like 1 million times slower. So it's a big problem. So the thing that BigQuery does is it applies various tricks to try to do a faster job of solving these kinds of big queries. So for one, imagine if you have one table that's very, very, very large and another table that's relatively small. So table 1 has, say, 10 million records, and table 2 has 100,000 records. Now, multiplying the two together is still going to give you that 1 trillion, right? 100,000 times 10 million is still going to be 1 trillion. It's going to be equal to 1 million times 1 million. Not really feasible. But what Google can do, they can take that one very large table and slice it into, say, 10 slices of 1 million each. And instead of multiplying those two tables together, maybe it just brings over a whole separate copy of that 100,000 record table and does that segment of the query locally on one machine. And then after it's done that with all the other slices of the big table, it can reassemble the query results and send them back. So there's different tricks like that BigQuery can use. So, there's not anything magical going on here. In most cases, it's just, a smarter solution to a problem that would be difficult for, most businesses to come up with and engineer and make sure it works correctly. And it's obviously going to take a lot of hardware. So an ordinary business would not want to take all the time and effort to design a system that big for the occasional very large query it might have to do. But Google, they design the system once and they sell the BigQuery service to a lot of businesses, so that BigQuery is kind of always in use around the clock. They're getting a lot more revenue back on that work that they did. Now, so, again, if you're interested in this stuff, if you're like, this database stuff sounds interesting, I would like to know more, I have some links there. By all means, check them out. Okay, but it's a little bit beyond the scope of, honestly, this stuff is probably even beyond the scope of IDS 410. Last I checked, they didn't even really cover NoSQL databases there, which is strange. But anyway, if you're interested in this stuff, yeah, there's some links. Now, difference between BigQuery and Spanner. So if you've just been half listening, you're probably thinking, wow, these things sound really similar. BigQuery can deal with big problems. Computer service call. I finally pulled the trigger and ordered my new Alienware desktop, but there were some hassles in getting the monitor delivered, and now they're following up with me. So that's what that was. By the way, in case anyone is wondering, that is a kiwi bird call, so it's very piercing and hard to miss. So, yeah. Indeed. Yeah. Anyway, difference between BigQuery and Spanner. So they can both process a lot of data very quickly. So what's the difference? Well, Spanner is designed for frequent but relatively simple database operations. Like somebody buys something and the database have to say, oh, you bought this and you gave us some money and now here's this entry on your credit card system, right? stuff like that that's fairly simple to do. BigQuery is good for relatively infrequent but really massive database operations, right? Imagine if you have a few years of historical supply chain data and you want to pick through it to find out what the best routes are, what the worst routes are, who your best drivers are, who the worst drivers are, that sort of thing. Okay, so BigQuery, you would use it for that. Spanner is more for small, simple tasks that happen frequently. Okay. Now, getting into like some specific usages of all this. Start with terms and definitions, and everyone likes terms and definitions. So, first one, data warehouse. This term makes sense, okay? Because it's just what you think it is. If a business had all of its data, where would it put it? It would put it in the data warehouse. That's what a data warehouse is. The second term does not make a lot of sense. I apologize on behalf of whoever came up with this. I never liked it myself. So a data mart is a subset of a data warehouse, typically corresponding to a specific functional area. And if back in the day anybody had asked me what term I thought you should use, I would have said something like an aisle or a shelf or a section. I would not have said a mart. To me, mart means a store, right? Where you go to buy data. I would say if you're buying external data from some other source, that's a data mart. So I don't like that term, but it is what it is. It's used. Now, as far as data, there's usually a natural growth process, a natural accumulation of data in organizations. So you have different functional areas, they accumulate data over time, and they tend to manage their own data, right? Especially in the pre-ERP era that we'll talk about. Now, combining data in one big storage system is pretty easy, but that doesn't get around the problem that you still need different permissions to access different parts of it. So if you say, yeah, we're going to have all of the data for our organization, and machines 1 through 50, those are going to be where accounting's data is, and machines 51 through 99, that's going to be where the manufacturing data is, and machines 100 through 200, that's going to be for our marketing data. Whatever, you still need permissions to get there. So the problem is, if you have that kind of permission-based system where specific users are allowed to access specific machines, it's really hard to integrate that with a website. So one of the big trends of the 90s and the aughts was creating a complete integrated system where people from the outside could make a transaction through a website and kind of get around some of those permissions. So I'll give you an example. We'll go to Paint. So here we have a manufacturer. Dun, dun, dun. There's suppliers. Oh, we'll use a circle for the suppliers. And you'll see why we need it in a minute. And then we have some retailer here. Okay. Retailer, supplier, and MFG for manufacturing. Okay. And the supplier sends stuff. All right, so say inputs. And the retailer wants to make a purchase inquiry. Okay. So, circa 1990, what would happen is the retailer calls up the manufacturer on a telephone, right? And they call Susie at the front desk. And they say, Susie, we got to get some bicycles. Christmas is coming up soon. Can you give us 1,000 bicycles by December 1st so we can have our displays all set up? And Susie won't have, what's happening here? You cannot see? Somebody did something. That was freaky. Okay, so Susie, she doesn't have all that information at her fingertips, right? She doesn't have permission either. So Susie says, okay, I'll talk to our manufacturing guys and they can talk to the suppliers and we'll see how much inventory we have and how much capacity we have and whether our suppliers can ramp up whatever to meet that request. And then I'll talk to our accounting guys. They'll see what sort of accounts payable, accounts receivable we're still waiting on from you. And then I'll talk to our finance guys and see what kind of credit terms we can offer. And I'll get back to you in 3 to 5 business days. And in 1990, that was fine. But 1999 rolls around, and now the business has a website. And the retailer wants to go to the website to try to place the order right away, right? Retailer doesn't want to call Susie and wait 3 to 5 business days. Retailer wants to go to the website and find out, within 3 to 5 minutes, whether it's going to be feasible. But in order to do that, he has to somehow bypass all of these permission controls in the databases. So you have to reintegrate everything somehow to say, well, okay, this retailer, he can ask questions about how much inventory we have or whether a certain order is feasible. He can look up his own status information and find out that, oh, you have, we're still waiting on payment for you from last year's bicycles. And he can look up his own credit terms online. So there's got to be some way that an outside user can get access to all that information without specifically going through the permission process for each different department. And that's essentially what ERP does. Now, we've mentioned ERP before, but I'll mention too, it comes out of, this is just historical notes. So MRP was the first one, Materials Requirements Planning. And that basically said stuff like inventory, capacity, inputs en route, right, being delivered. And the thing that MRP would do, it would say, is this order feasible, right? If you order 1,000 bicycles, can we even provide you with that order? So MRP was the first thing that people came up with. MRP2 was basically this ordinary MRP plus, transactions. I was going to say finance and accounting, but I'll just say transactions. So you can do payments with MRP2. So it's going to link together with accounting and finance. And then ERP, in a sense, MRP2 plus everything else. So ERP takes all of this data, all of these systems, and brings it into one common system that anybody can access and see the stuff that they're supposed to be able to. Okay, so that was the progression. ERP, people didn't just wake up one day and say, oh, we need ERP, let's invent ERP. It was, part of a progression. Okay. So normally, if you took an intro to MIS course, they'd probably have a whole chapter on ERP, and they'd spend a lot of time talking about the history and why it happens and a little bit of a deep dive into how it works. But at this point in time, you kind of all you need to know, since most businesses will have it. The vast majority of you will go to work in a business that has an ERP system. And so what you really need to know at this point is what it does and why we have it. That's pretty much, and that's what you get. So ERP systems integrate all the data from a business into one common system, enables faster and more accurate decisions, right? So you don't need to push requests through other departments. You don't run into the problem of inconsistencies across departmental databases, right? Imagine if, the accounting guys, they should have updated some transactions for you, right? They should have recognized that you paid your bills, and that should be reflected in the system, but they had some kind of lag and they didn't do it. So when when the retailer goes to talk to Susie, Susie says, oh, sorry, we have this bill, from 3 months ago that you haven't paid, so we can't give you any credit at this time. And then, the retailer's like, well, we paid you guys. That's a sort of inconsistency across databases that can happen. So ERP is supposed to prevent that. Anyway, current usage, practically all large businesses have an ERP system, and a lot of medium and even small businesses do now as well, because the costs have come down quite a bit. All right, last few slides we're going to cover supply chain management and some related topics. So supply chain management is basically getting stuff to where it needs to be on time, in the right amounts, tracking it, making sure it's paid for, all of that kind of stuff. So as a business function, supply chain management takes inputs from all over the organization. So for example, marketing can tell you what demand is going to be and whether it's trending up or trending down. So you need to know, how much capacity you should have available for shipping. As far as accounting, right? If supply chain management is managing these transactions, well, that's where the accountants come in. And of course, operations, right? If that retailer shows up and, goes to your website and wants to order 1,000 bicycles, needs to know, hey, how much capacity do we have? How much inventory do we have in hand? How many bicycles are, in the works? How many inputs are coming in from our suppliers? Can we get more if we need them? That sort of question. And if we can get more, do we have available worker capacity to assemble them, or are we fully booked through December 1st and we just have to say, sorry, we're fully booked. Anyway, an ERP system should provide high database consistency, right? Prevent any sort of conflicts, because any answer to any question is going to be there in one place. enables all kinds of fast and correct supply chain management decisions. So you won't have the case where a retailer goes to your website, tries to place an order, and there's some aspect of his data that's wrong, and he gets the wrong answer, right? That's what you want. You want them to get the right answer. Okay, now we're going to take a step into virtual machines and some other stuff, and then we'll talk about supply chain management in the cloud. So virtual machine, the term breakdown. So virtual means a computerized version of something, right? So virtual servers that we've talked about with cloud, or virtual reality. Maybe some of you have an Oculus at home, whatever. And of course, a machine just means a computer. So a virtual machine is the equivalent of a single standalone computer, right? But it might involve hardware and software that are present on many other separate machines. So for example, if you say to some cloud system like Amazon, I would like to rent one server equivalent, it doesn't necessarily mean you have exclusive use of a particular machine. It means you have a set of functions scattered throughout the cloud that in total are what a single server could do. Okay, so that's what a virtual machine is. Now, cloud systems are built around virtual machines. Number one, so users generally don't need to know the internal details of how the cloud works, right? Outside users don't need to connect to a particular machine. They just need to be able to connect to where the cloud has whatever information they're looking for. And that gives also the cloud flexibility to assign or reassign resources. So if you have some data that's being very frequently accessed, cloud might cache it or might put it on, some kind of higher end machine. If it's some kind of data that probably nobody's ever going to look at, like tax forms from 5 years ago, probably nobody's going to look at most of those. Yeah, they put it on some much slower, cheaper portion of their system. All right, so here are a couple more slides. We'll talk about migration. So migration that's the technical term for when you're bringing all your stuff to the cloud. So as our scenario here, there's a business that manages all of its supply chain processes internally using its own hardware and software, right? It's got its own systems for that. But it generates a lot of data. And so they're looking at shifting it to the cloud because it's getting to be a hassle. It's branching off into multiple machines. They don't want to design a separate system that's going to have to, bring together all this information, all these different machines. They just want to focus on selling shoes or whatever. So they want to run the same system, but in the cloud, to allow for future expansion. And big concern, the supply chain system can't ever go offline. You can't have a week or two where you say, sorry, nobody can check the status of anything because we're moving it to the cloud. So you got to keep the one under your roof running the whole time as you're building the one in the cloud. So the big picture process, number one, each component in your internal system, you're going to somehow copy that to a virtual machine in the cloud. Right? And once you've done that for all of them, boom, you have a copy of your system in the cloud, right? All the components are supposed to be functional there. Then you copy all your data. So you start feeding data into the cloud. And once you've got that system set up, you have to play catch up, right? Because there's going to be, a few days of real data that you've gotten. You have to start sending that to the cloud. And pretty soon, once you're done with that, you have to be sending data both to your internal system and the cloud system at the same time. While that's going on, you're going to be testing all the different component and system functions, right? You're going to ask yourself, is this working the way we thought it would? Is it working as well or better than the system we had under our roof? And when you're finally happy with it, when the cloud-based system works satisfactorily, you start using the cloud system and you pull the plug on your internal system. You say, yep, we're just going to cloud now. Ta-da, and you're done. Okay, that's how it works. So you build the system in the cloud, you feed it all your data, you run a bunch of tests on it, see if it's working the way it's supposed to, and once you're happy with it, boom, you're done. Okay, now, supply chain management operations do tend to generate lots and lots and lots of data. So if you think about every shipment that an organization does, right, chances are they're not just recording the start and the end points. They're not just recording, oh, this pair of shoes left our factory, on January 1st, 2 p.m. and arrived at its destination January 4th, 5 p.m. There are probably going to be a lot of intermediate data points for every shipment, right? You might have some system that takes readings at like 10-second intervals across the whole length of a trip, meaning that you're very rapidly going to end up with these massive database tables like I was talking about with BigQuery, right? is very, if you have a separate record for every data point on every shipment, that's going to add up pretty fast. And the problem is those database tables can take a very, very, very long time to run queries on, especially if you're doing queries involving other tables, right? If you're just looking up stuff in one table, it's not so bad. That's fast, like pulling a photo out of Facebook's haystack. But if you're running relational database queries, across multiple tables, things like which of our drivers are the best, which of our routes are the best, are there times of day or times of the year or weekdays where one route is better than another, right? If you're trying to do that kind of stuff on these very large tables, it's going to be super, super slow. Or you can design your own massive custom system, which again, these businesses mostly don't want to do. So business can use both BigQuery and Spanner to deal with some of these problems. Basic workload division, if it's something small and simple, like if it's recording a data point on one of those trips, probably do that with Spanner, right? BigQuery, number one, it's for queries. And number two, it would be like, I don't know, using an aircraft carrier to, I don't know, carry your grandma across a creek. I don't know. It'd be overkill, right? But Spanner's good for that. Spanner's good for those little tiny transactions. It's what it's built for. Other things that need to happen fast, right? If it's a real-time update, if there's a new update on the status of some shipment, you want your users to be able to go in and check and see that something is where it's supposed to be. If a payment happened, you want that to happen in real time, pretty much immediately. Nothing goes wrong with that. So those kind of things, again, need to be super fast, super consistent, happen in real time. You want to use Spanner for those. But BigQuery has its uses, and one of the main uses for that is if you have a massive, massive set of this supply chain data and you want to do some big queries on it to try to figure out how to best, structure deliveries or delivery routes or assign drivers, whatever, that's the sort of big problem you would use BigQuery for. Okay, I'm going to mention one other thing, because another way where businesses can generate massive amounts of data is web analytics. So imagine if you have a successful website and you're getting like 1 million visitors per day. Well, with web analytics, you want to track what visitors are doing when they get to your site. But if you have 1 million visitors in a day, every one of those visits becomes a record. So you're getting 1 million records a day at a minimum. And then expand that over the course of a year, very quickly, you have this massive amount of data that an ordinary business, even though, yeah, they have a website and stuff, they don't want to develop the kind of custom database system to deal with that. So the very big operations that use Google's premium web analytics service, BigQuery is built right into that. So they got to pay for it. But, if your business is getting like 1 billion website visits per month, you don't want to design that custom service yourself. You'd rather say, oh, we'll go to Google, they have it, it works, it's fast, it's great, done. Okay, that's all I have to say about that. If anyone has any questions, you are free to ask. Otherwise, remember, Wednesday will be our usual review session, so bring questions if you have them. That's what we'll do. Okay, have a good day.